Hello, today we are going to design of a combined trapezoidal RCC footing. Here two columns are given. I can call it C1 and C2 with a size of 400 by 400 and 600 by 600. Having the weight or the load coming on that column is 800 kilonewton and 1200 kilonewton respectively. These are all working load. I am not talking about the design load as such. The center to center distance between the two columns is already given as 4 meters, and the edge distance from the center of the column C1 to the left of this C1 is 0.8 meter, and the edge distance of the second column C2 from the center to the right of the extreme edge is given as 1.2 meter. One thing that you have to keep always in mind, when the length is given, edge distances are given, means that cannot be designed as a rectangular footing, but it is to be designed as a trapezoidal footing. Because of some restrictions in the length, because of some boundary conditions, boundary parameters, we will have to go for the design of the footing as a not as a rectangular but as a trapezoidal one. So we will have to calculate the dimensions according to the parameters given. The other parameters are, of course, M20 Fe415 as usual. And now, when we start with this, we can see the load is given as 800 and 1200 kilonewton. So we can just calculate the area of the footing in nothing but W1 plus W2 plus 10% of W1 plus W, that is called the weight of the weight of the footing, and it comes out to be 2200. 800 plus 1200 plus 10% of 2000. It comes out to be 2200. 22,000 divided by the bearing capacity of the soil. Of course, I have not mentioned there at the time of explaining about the parameters. Another parameter which is important is the safe bearing capacity of the soil is given as 160 kilonewton per meter square, safe bearing capacity. So we are just calculating the area required. We just calculate the area required by the total load of 2200 divided by the safe bearing capacity. It comes out to 13.75 meters square. Rounding it on the higher side, I call this as say 18 meters square. 18 meters square. Now, once we can find out this, the next part is to complete the trapezoidal part, and that can be seen over here. Yes, see, this is column C1, this is column C2, having a load of 800 kilonewton and 1200 kilonewton. Center to center distance, this given as 4 meter. This distance is 0.8 meter, and this distance is given as 1.2 meter. So definitely the total length which is given is equal to, automatically comes out to be 6 meters. Now, once the length is known, now we'll have to calculate the area required. We have already seen that area required is nothing but 18 meters square, that we have seen on our previous page so far. Now, these parallel edges are undefined, yet to be calculated. So we'll have to calculate these two perpendicular distances, this at this edge as well as this edge, because this length is known. So area of this trapezium is nothing but half sum of the two parallel sides into perpendicular distance between the two. That is A plus B by 2 into L. That will give the total area, and that must be equated with the total area of 18 meters square. And once we know that the area of trapezoidal A plus B by 2 into the perpendicular distance, we can find out the area required in terms of A and B, and it is A plus B by 2 into L is equal to 18. A plus B is equal to 18, so A plus B is equal. So this is the equation number 1 in terms of area that we have calculated. But still A and B are unknown. A and B are still unknown. Just to calculate this unknown A and B, we will have to search out some another equation in terms of A and B, so that two unknowns, two equations, and then A and B can be very easily calculated. For this again, we will go over the same concept, that the CG of the load should coincide with the CG of a combined section. CG of the load. First of all, we will calculate the CG of the column load from this edge. Previously, we were just calculating the CG right from here, but in this case, it is more convenient to take the CG right from here. That is W1 into 0.8, that is 800 into 0.8 plus 1200 into 4.8 divided by sum of the two, that is 800 plus 1200, that will give the value of CG, and that we call as X bar. X bar can be calculated. That is, I have of course multiplied by 1.5. I will not divide it because it is also to be divided by 1.5. It makes no difference. So 800 into 0.8 plus 1200 into 4.8 divided by 800 plus 1200, because 1.5 will cancels out, X bar comes out to be 3.2 from here. 3.2 from here. This now we have to see that CG of this section should coincide with 3.2 from here. So calculate the CG right from here. That is how we can find out the center of gravity of the trapezium section when A and B and L is given. But simple formula, A plus 2B upon A plus B into L by 3. Yes, using this mathematical expression, A plus 2B upon A plus B into L by 3 must be equated with X bar of 3.2. Now, with the help of these two equations, this is equation number 2. This is equation number 2. This is equation number 1. This is equation number 2. With the help of these two equations, now we can very easily calculate value of A and B, and it comes out to be, A comes out to be 2.4 meter, A comes out to be 2.4 meter, and B comes out to be 3.6 meter respectively. That you can see right from here. This page itself shows. And now you can see this is 2.4, this is 3.6, this is 0.8, this is 1.2, total distance is 6 meter. And now we can see, yes, in these circumstances, the CG of the load is coinciding with the CG of the section for even distribution of the upward pressure of a soil. Now, up to this, there is no problem as such. But now here, the section is varying at any distance. Previously, when we were talking about the rectangular section, it was constant right from here to here. But in this case, this is varying. So that cannot be applied over there. So what we have to do is, we have to find out this distance at any distance from X. I can call it the Bx. The distance of bx, width bx at any distance x from here. Because this is at all the times it is required when we are calculating the area from here to here, here to here, here to here, here to here. So at all the times we are supposed to know this height, this distance. It is better to go for some mathematical expression and find out the general equation for finding out the width of this section at any distance x from here, and it will be nothing but comes out to be a plus 0.2x. bx is this width at any distance x, and it comes out to be a general equation that I am framing so far just to find out this width at any distance x from here. Substitute the value of x and you will find the appropriate width over here at any distance. Just for example, whether this is right or wrong, let us check it. If I put x is equal to, you must get 2.4. This is A and this is B. We have seen already A is already 2.4 and B is already 3.6. Let us substitute the value over here. First put x is equal to 0 and A is equal to 2.4. Yes, it is true that it is given. If I put x is equal to L, that is 6 meter, then put over here and confirm it is 2.4 plus 2 times 6 and it will be 3.6 meters. Means this is the general equation that we have framed so far, and by this equation we can straightway find out the ordinate over here at any distance x from here. Now we have to calculate the area of this trapezium. Again it is a complicated one. So have another more second equation just to find out the area, and that will be mentioned over here. That is a into x plus 0.1 into x square. Substitute the value of x and you will find the total area up to that point where we are considering the value as x. Suppose this is your x, then I am finding the total area of this one. Let us confirm whether I am right or wrong. If x is equal to 0, area will be 0. If x is equal to 6 meter, you must get 18 because we know the total area is 18. That is 2.4 into 6 plus 0.1 into 6 whole square, that is 36. And you will find it comes out to be 3.6 meter. And then you get 18 meter. That will comes out to be 18, means the general equation will solve the purpose. So this is the second equation. I am repeating these equations that we call the general equations for finding out the width at any distance x, the area under that curve between that x and an original A. Similarly, we will have to find out the third equation for the CJ of the section from this edge. That is x bar now. CG from here for this section. If at all this is a trapezium section, then CG from here we can as x bar. Again we will have another equation just to find out the CG, that is 3a plus 0.2 of x upon 2a plus 0.2 of x whole into the bracket close into x by 3. This is the most important because we have to find out the CG at all the times at every section where we are taking the moment. So if this is the value of x, then CG from here can be calculated directly by using this mathematical expression as 3a plus 0.2x upon 2a plus 0.2x bracket close into x by 3. Substitute the value of x and you can confirm, put x is equal to L and you can see, you know the area of CG, A plus 2B upon A plus B into L by 3, it will be 2.3 from here. So this equation is an important equation. I can call this is the third equation. This is the third equation that comes into picture. First, ordinate, then area under the curve, and CG from that ordinate to this side. Now, once all the three equations are known, general equations that we have found out so far, now our next part is to find out the shear force. Shear force at any section, and then we have to draw the shear force diagram. Before we find out the shear force diagram, first of all, we are supposed to know the upward pressure. Upward pressure is nothing but total load divided by the actual area. Now here we start taking the design loads instead of the working load, which was already given as 800 and 1200. So here instead of 800, now we will go for 1200. 800 into 1.5, that is 1200, and this comes out to be 1200 into 1.5, that is 1800. So W1 plus W2 upon total area of 18 meters square, then that will give the net upward pressure of soil as 166.67 kilonewton per meter square. It comes out to be 166.67 kilonewton per meter square. Once the upward pressure is known, then we can very easily calculate the shear force. We can very easily calculate the shear force at any distance from here. How? Upward pressure multiplied by that area will give the force. That is the shear force. But this is only applicable up to certain part. As soon as I am crossing this is to be, this load of 1200 kilonewton acting upward is to be subtracted. This is upward pressure of the soil, and this is downward force because of the load. Now, after finding out the upward pressure, now we start calculating the shear force at every section. That is, at this section, at this section, at this section, and at this section. We'll find out the shear force in 2, 3, and 4. Not even that. We'll have to find out that particular point where the shear force changes the sign from positive to negative at any distance x from here. So we'll have to find out that value of x where the shear force changes the sign, or shear force upward pressure minus downward pressure must be equal to 0. Sum of the two equal to 0. So we'll have to find out the shear force right from here, 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 as well as at that point where the shear force changes the sign from positive to negative. Now we'll just proceed ahead accordingly, and I am giving a general equation for finding out the shear force. And in which we will find upward pressure into equation number 2, which indicates the area. Equation number 2 in the area. So, area into upward pressure will give the force. Yes. Pu into equation number 2. This is minus because it is giving upward pressure. This is only applicable just at the left of column, center of the column W1. That is C1. As soon as I am coming to C1, then this is to be 9, this is minus, this is plus. So total shear force at first column center will be upward pressure into equation number 2, which is with a minus sign, plus W1. And this will continue up to just to the left of W2. As soon as I am reaching to W2, then in addition to that, this is to be taken at W2 also. Now, step by step, you can proceed ahead. First of all, start calculating the shear force just to the left of section A, that is just to the left of section A, say lower column A, that is first of all find out the ordinate over here, then the area over here, then pressure into area will give the upward force, and that will be just to the left, and just on this one it will be minus W1, and you will find it comes out to be, the values can be calculated, and the shear force diagram can be drawn like this. As soon as I am starting from here, shear force will be, x will be 0, automatically it comes out to be 0. It reaches the upward pressure going negative. Here this is going value. Then here you can find that there is a downward force of 1200 kilonewton, it is so downward. Again it goes like this. Again downward of 1800 kilonewton, it reaches to 0. Because it is a square term is though, that's why it is a curvilinear shape and not the straight line as we are talking in terms of a rectangular footing. So we'll have to find out this point also, where the shear force is 0. Find out first of all point of x. Find the point, that is Pu into x minus W1 must be equal to 0. Again I will just show you this figure. Upward pressure into this much area of distance x minus W1, minus this plus W1 must be equal to 0, so that here you will find the shear force is 0. Find out the value of that value of x, and it comes out to be 2.6 meter from here. If you find, you will find 2.6 meter from here. Once we can find out, means we will have to find out now the shear bending moment at this point, as well as this point also. We will have to find out 3 bending moments, and for that bending moment now we will have to go ahead for next part, that is for bending moment calculations. Now again I will start with general equation. What is bending moment? Upward pressure into area into Cg. Upward pressure, we know that is 166.67. Area of the section at which we are just calculating the bending moment. And the equation, that is equation number 2, that is Ax plus 0.1 x square. Put the value of x at all the times, and the third equation of x bar, that is pressure into area will be the force multiplied by the Cg will give the moment. Using this general equation at all the times up to W1, this is true. But as soon as I have crossed the value of first load W1, then it will be minus something, I guess, that is minus W into x minus A. That I will come over here, next part. That is bending moment at A is 0, definitely bending moment at D must be 0. Now bending moment at any distance x will be, now you can see, this is upward pressure, this is area, and this is Cg. Where we have taken this? We have taken this bending moment at x is equal to 0.8, means the center of the left column, that is C1, and this comes out to be this much value. As soon as now I cross the value of this W1, that is column C1, then I am coming across that particular point of 2.6 meters, was it a 2.6 meter? Yes, it was 2.6 meter perhaps. Let me confirm. Yes, it was a 2.6 meter. We'll have to calculate the bending moment at a distance of 2.6 meter where the shear force is 0. Now, similarly, just calculating the value of that distance at a distance of 0.8 meter, then at 4.8 meter, that is at column B, and then at third point, that is at a distance of 2.6 meter, again pu a into x bar, 166.67. Calculate the value x bar by using the formula ax plus 0.1 x square. Using this formula of x bar, that is 3a, it is 3a plus 0.2 x upon 2a plus 0.2 x into x by 3, and you will find minus, if this is minus, then plus w1 into x minus a, x minus o. That is, I am talking about this distance. I am talking about this distance, or I can say, if I will go through this figure, this is w, this is this distance, w1 into this distance, that will be plus, and upward pressure into area into Cg will give the minus 1. And you will find the three types of moments are there. Maximum bending moment you will find at O, that is where the shear force changes the sign from positive to negative at a distance of 2.6 meter from left edge. Now, after finding out, you just draw the shear force diagram and then draw the bending moment diagram. You will find this is the bending moment diagram. This is the bending moment diagram. Here you will getting the one maximum bending moment, another maximum bending moment column at this is column A C1, this is column C2, and this is that point of 2.6 meter. This is 0.8, this is 1.2, this is 4, and total is 6 meter, and this is 2.6 meter, which is maximum, and then it decreases like this. So for amongst all the three, pick up the maximum bending moment and find out the value of D required. Find out the value of D required. And using m is equal to RBD square, using m is equal to RBD square, mu max is given as 711 point something, 0.06 kilonewton meter. B will be taken as 1000. R will be 0.138 into FCK because FM20 is given. FCK will be 20, and find out the value of D. And when we find that D comes out to be 507 point something mm. Rounding off, capital D, overall depth 600 and effective D 540, which is greater than 4507, so it's okay. Now, after finding out the depth, find out the area of steel, find out the area of over for this bending moment, for this bending moment, for this bending moment, and the diameter and the spacing. You can find out the area of steel at this point, and at this point, because we know that three bending moments are known. Three bending moments are known. So find out the bending moment first, and then depth, and then comes out to be area of steel at B, area of steel at C, and area of steel at O. A, B, C, D, and O. B is the point where the first column is applied the load. C is the load of the second column. D is the edge. A and D is the left and the right edge. Then A, C is known. Use the diameter and call the spacing. The spacing can be very easily calculated because the maximum bending moment will be at the midspan over here. So you will have to use at least 20 or 25 bar diameter, and then you have to calculate the spacing. Under any circumstances, you will have to see that the spacing should not be less than 100 at any cost. If it reduces to 100 increase the bar diameter and just calculate it. Once this is known, then we will have to go for the next important part. Next important part is the transverse reinforcement. We'll have to, because we have calculated the reinforcement in this direction now, in the bottom. Now we have to go the reinforcement is that the transverse reinforcement. Now finding out the transverse reinforcement, again we'll have to find this distance. Because this is the minimum distance, this is the maximum projection. So we'll have to find out this maximum projection. It is nothing but, first of all, find out this distance by using equation number 1. Out of this, minus 0.6, that is 600, and upon 2 you will find this distance. You can find out this distance, and once this distance is known, it comes out to be 1.38. This is the upward pressure multiplied by 1. It will give kilonewton per meter upward pressure. And this is the distance. It is exactly same as cantilever with a uniformly distributed load. You can state by finding the maximum negative bending moment is WL square by 2. And it comes out to be this much. Again, consider the diameter and find out the area. And find out the area spacing. Area and the spacing of the bar. After this, we will have to apply one important check, that is check for punching, that is two-way shear. As we know already that the punching or the critical shear takes place at the distance of effective d by 2 from the face of the column. So if this is the column face of giving 600, then d by 2 from here, 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 it comes out to be, just see, 0.6. Then this is d by 2 and this is also d by 2, it comes out to be 1.14. This is 1.14, this is 1.14. Now we'll have to find out the net force, that is Vu. Vu can be calculated as this downward force of 1800 kilonewton minus upward pressure into the hatching. The only portion that is we have to consider is only this much portion. Only this much portion. Not full. So how this can be calculated? 1.14 into 1.14 minus 0.6 into 0.6. This is to be subtracted. Exactly same thing it has been carried out over here. That is 1.14 into 1.14 minus 0.6 into 0.6 multiplied by the upper pressure. This will give the value of Vu in kilonewton. Tau Vu can be calculated as nothing but Vu into 1000, that is Newton. B is nothing but, it is B dash nothing but the sum of the parameter of the four sides. That is 4 times 1.14 B into D. This is converted into meter, and again this is already D is 540, and it comes out to be 0.62 Newton per mm square. So tau Vu comes out to be 0.62 Newton per mm square. How we can find out the tau C? Then we know that K times tau C should always be greater than tau V. And K will be nothing but 0.5 plus beta C. 0.5 beta C comes out to be 1. So it will be greater than 1. So we are considered K is equal to 1. And how we can find out the value of tau C? Tau C is calculated with 0.25 under root of FCK. It comes out to be 1.18 Newton per mm square. So 1 into 1.18 Newton per mm square is greater than 0.62 62 Newton per mm square, we can say yes, it is safe, so it cannot be penetrated, and it is safe for the punching also. That's over and all about the trapezoidal combined footing of the RCC. Thank you very much.